Hi, I'm Chi-Ming, an AI engineer from Mediatek. Today I'm going to share our work, check low-power violations by using machine learning-based classifier. First, let me introduce the background. The violation check process for design verification involves iterative simulations to ensure design's correct functionality and behavior before it steps out. In each simulation iteration, the violations are output to flag suspicious conditions. Designers need to manually review violations, which are either false alarms or design issues that must be fixed. Though these bugs account for a small proportion, the review process still requires cross-team expertise of design domain knowledge and lots of time to investigate violations. As the complexity of a design increases, designers may miss detecting design issues after RTO freeze due to the overwhelming workload of the violation review process, especially in a limited time. This usually induces engineering change order process. Here comes our objective. We present a solution with a machine learning-based AI checker to identify highly dubious violations. The violations in IC design check flow are composed of tests. The words in the signals usually represent certain physical characteristics. These machine learning techniques have the capacity to learn and identify design issues by analyzing the content of violation logs from a vast collection of simulations. We aim to reduce manual review effort on violations and shift the bugs left, making bugs solved earlier. We propose 3 steps to learn an AI checker for violation classification. There are data preprocessing, feature engineering, and modeling. First, we process the historical data so that they can be used for machine learning. We have violation logs obtained after mating simulations. We remove the noise, such as word capitals, digits, and special punctuations. Next, we tokenize violation logs and parse the logs into tokens. Machine learning algorithms cannot work with raw text directly. Therefore, the text must be converted into numbers. Specifically speaking, vectors of numbers. We represent violation log texts as bag-of-word vectors. A bag of words is a representation of text that describes the occurrence of words within a document. We use it to encode each violation log. These columns are the union of all violations tokens. We concatenate these bag-of-word vectors with bug labels for all violations to get document term metrics. Next, we further utilize the feature engineering technique to incorporate more physical characteristics into the document term metrics. We have 2 custom features. First one is novelty feature. We define new tokens which do not appear in historical tokens as novelties. To locate these novelty tokens, we construct the distinct token sets from historical waived violations and new design violations. Then we compare the differences between them. Only tokens that appear in the new design will be defined as novelty tokens. For a second feature, when constructing the document term matrix for machine learning modeling, we use common tokens to align training and testing feature sets. For the tokens that only exist in the training or testing dataset are invalid for modeling. These tokens are called non-common tokens. That means we may lose important information because the tokens shared with similar word structures usually have similar physical significance. Therefore, we created a feature to utilize and extract information from these non-common tokens called token clusters. In implementation, we group these non-common tokens and assign each of them for each violation to one cluster. We make sure the the occurrences of clusters for non-common tokens in each violation and generate features. Lastly, for modeling, we learn an ensemble model for different datasets using cross-validation techniques. We integrated the views of all models to obtain the final classification result. For the experiment in result section, we apply the proposed approach to isolation claim value check process of 3 different low-power designs, including design A, B, and C. ISO claim check flow is a key flow in each project that integrates more than one power domain. In multi-power domain system, we should insert ISO cell on the signal that drive value from power off domain to power on domain. The ISO cell always ties to either 0 or 1, meaning ISO low or ISO high cell. If wrong ISO cell is selected, system may hang up during power on or power off procedure. These violations were generated by simulation tools during project development. In addition to the isolation check used in this empirical study, other types of checks that have violation signals consisting of tokens of text are all potentially applicable using our approach. We presented the ablation study with our approach to give an intuition of its behavior and performance. We used recall rate and reduction rate to validate the performance of AI checker. The recall rate denoted the ratio of the number of true design issues in the predicted high-risk violations divided by the number of total true design issues. The recall rate equal to 1 indicated that the predicted high-risk violations contain all true design issues. The review reduction rate represented the percentage of low-risk violations from the review process. In practice, designers have no need to review low-risk violations identified by AI checker. We could observe that as more methods joined in, the recall rate was closer to 1, and the review reduction rate went down. There was a trade-off between the recall and review reduction rate. In the end, we could achieve respectively 50%, 12%, and 18% review effort reduction for designs A, B, and C. For our conclusion, our work proposed an approach that applied machine learning techniques to assist the violation review process and presented the empirical study on the isolation check. The result demonstrated that we could reduce at least 12% and up to 50% review effort without human experts' involvement while detecting all design issues. It achieved the shift left of design issues so domain experts could tackle more bugs in the early stage. We could also train the model incrementally using accumulated historical data. Hopefully, starting from the promising result of 3 designs, we proposed AI checker can be generally applied to other design check flows. Thank you.